Now let's take a look at the so-called Michelson-Morley experiment. We have done an experiment in 1C called the Michelson interferometer. It was invented by Michelson for the purpose of measuring the speed of the Earth going through the vast sea of ether. And the original Michelson-Morley experiment was far more intricate than the one we did in 1C. And here is a schematic diagram of the setup. I have a beam of light coming in, and it splits two ways after going through this half-silvered mirror. Part of it gets reflected this way, getting bounced back to mirror 1 and eventually going to the telescope. Another one passes through the half-silvered mirror, get bounced off by mirror 2, and eventually come back here. Now, assuming for simplicity that arm 1 and arm 2 have the exact same length L, then if the Earth does not move relative to ether at all, then the speed of light measured either this way or that way will be the same. It's just c, whatever that constant is, right? And since they travel the same distance, they're going to arrive at the telescope simultaneously, and therefore they will be exactly in phase, and you will have a bright spot. Now, suppose the Earth moves through ether. There is this called ether wind, which means this is how fast the ether moves relative to the Earth. In other words, the Earth actually travels this way, through the sea of ether. Okay, so this is v of Earth relative to ether. So this v is the speed, the velocity of the ether relative to the Earth. Now, let's see. This beam coming in, as it traveled to M2, relative to ether, how fast does it move? Well, it is moving on, it's riding on Earth, which itself is moving this way, relative to ether, right? So it's like a car shooting a beam forward while moving forward. So relative to ether, it actually travels at a speed of c plus v, okay? c plus v. But as it comes back, you have to go c minus v because it's the other way around. On the other hand, look at that beam, okay? Now, this is a little complicated because the beam travels this way relative to the Earth, and yet the Earth moves relative to ether that way, so there's a 90-degree angle between these two velocities. You have to use vector addition. But suffice to say that the speed of the beam relative to the Earth going through arm 1 and arm 2 would be a little different, right? A little different, which means traveling through the same distance as they come back and get collected at the telescope, they will arrive not simultaneously anymore. And as a result, it could go out of phase, or at least slightly out of phase, and you're going to see some fringe movement as a result. Okay, now let's take a closer look. I have here a vector diagram for velocities. There are three velocities. VBE, which is the velocity of the beam relative to ether, it equals VB Earth plus V Earth to ether. This is how fast the Earth moves relative to ether. Okay, the ether moves towards the Earth like that, and that's velocity V. So these two differ by a negative sign. All right, and clearly from this diagram, the magnitude of the velocity of the beam relative to the Earth, which is actually the speed of velocity of beam number 2, which is where we're interested, equals to this speed squared minus that speed squared, and then the square root, right? And this is the speed, the magnitude of this vector is the speed of the beam relative to the ether. And by definition, that is c, isn't it? Because in ether, and only in ether, relative to ether, the speed of light is c. Okay, so it's c squared minus v squared. Now, let's take a look at the time difference. The time it takes for the beam to go through arm 1 and travel back, and then the time it takes for beam to go through arm number 2 and come back. They're not going to have the same speed, so they're going to arrive at the telescope at slightly different times. Okay, you look at arm 1. Going up and going down, the speed is the same. Okay, relative to the Earth, they're both equal to VB Earth. Okay, whether it goes up or down. But if you look at the speed of the beam relative to Earth going through arm 2, on its way there, it is riding on Earth, which is moving relative to ether. So it's like a shooting a beam forward while you move forward. So the speed relative to ether is v plus c. Going back though, it's v minus c relative to Earth, because the Earth is trying to escape that beam of light. So it's a c minus v, I should say, c minus v. Okay, so the total time it takes for the beam, for this beam going through our window, go up and down, would be 2L divided by the speed, which is the square root of c squared minus v squared. 2L because it goes up and then down. The total time it takes for the beam to go this way and back is L divided by c plus v, then plus L divided by c minus v. Okay, this is going this way, this is going that way. So there's a time difference between the arrival of beam number 1 and arrival of beam number 2 to the telescope, and here is the time difference, delta t. Right? This time minus that time. Now, we're going to make some approximation here to make our final result a little bit easier. And the approximation we're going to make is 1 plus x to the power n is roughly equal to 1 plus nx, valid for any n, and when x is very close to 0, which means the absolute value of x is very much less than 1. This is true if we define x as v over c or v squared over c squared. Either way, x is indeed very small because v is far less than c. So for the first term, what I did was I took that c out. Okay, what's left is 1 minus v squared over c squared to the power -1/2 overall. All right, and this can be approximated. X is equal to negative v squared over c squared. Okay, n equals -1/2, so it becomes 1 plus nx, this is v squared over 2c squared. Now what I did here was I combined these two terms, so it's v squared, c squared minus v squared, and upstairs is 2lc, and then I took that c squared out, so cancel with 1 power of c, so I get 2l over c, and what's left is 1 minus v squared over c squared to the power -1, not -1/2. Okay, so again, I use the approximation with n equal to 1, I'm sorry, n equal to -1 and x equal to negative v squared over c squared, and that's what I got. This term cancels with that term. What's left is, you combine these two, it's negative L v squared over c to the power 3. The negative sign doesn't really matter, it just tells you which beam arrived first. The difference, the importance is the time difference. Okay, if one of the beams travel faster than the arrived first, it's going to be a little bit out of phase from the other beam. Now, in reality, we don't really know whether the Earth moves this way or that way relative to ether. Okay, but suppose it moved this way. We're going to get this, right? And then what Michelson did was something very clever. He rotated the entire device by 90 degrees. Okay, he rotated 90 degrees. So now mirror 2 becomes mirror 1, and mirror 1 becomes mirror 2, and as a result, delta t would be reversed. Okay, so if delta t was positive, now it's going to be negative by the same exact amount, right? So I don't really care whether ether moved this way or it actually moved that way. Either way, when you rotate it by 90 degrees, the answer will be exactly reversed. So the total time difference for the two beams to arrive with or without the rotation will be twice as much. Agreed? Twice as much. So we look at a total difference. Okay, I'm going to take the absolute sign because it doesn't really matter which beam arrives first, which beam arrives second. So that's 2. There's a 2 here. There's a 2 here. Now, we can translate the time difference into a visible shift in the fringe, because every time one beam arrives faster than the other, it's going to produce an extra movement, which is a fraction of wavelengths in this case, and that can cause the fringe to shift. Now the beam travels with a speed that is very close to c. I mean, I don't care if c plus v or c minus v, it's almost equal to c. And therefore the extra distance one beam travels over the other will pretty much be c times the time difference. Okay, so how much would that be? That would be whatever this value is times the speed of light c. So we would say one beam would travel ahead of the other beam as a result of rotation by about speed of light c times delta, that 2 delta t we just calculated, which is 2 L v squared over c to the power 3. And how does that result in any fringe shift? Well, every time delta x equals one whole wavelength, it's going to go from one fringe to the next. So if delta x is a fraction of lambda, the pattern will move by a fraction of the fringe, and that fraction is delta x over lambda, right? And that is roughly equal to 2L v squared lambda c squared. Okay, that's the fractional shift. If that, again, that fraction equals 1, you're going to see a whole shift, a whole wavelength. So we can do some numerical calculation based on the setup. Lambda was equal to 11 meters, and the reason why you can get such a long arm was because they used multiple reflections. It was a very intricate device, as I said. The wavelength of light they used has a value of about 500 nanometers. And the c, of course, the speed of light, 300 millimeters per second. You plug all these numbers in, and you'll find the shift will be 0.44. Okay? So you will find that as you rotate this device by 90 degrees, you're going to get a little bit less than half of a fringe shift. That's expected. Of course, you have to know what v is, and we have assumed v here to be the speed of the Earth going around the sun, and that is about 34 kilometers per second. Okay, that's the assumption that we use. That's expected, 0.44. Now, was the device accurate enough to detect that kind of shift? Oh yes. It turns out that Michelson and Mollet built this device to have an accuracy about 1/10 of a shift. Okay, actually 1/100th of a shift, 0.01 fringes. You expect 0.44. That's 44 times the maximum measurable accuracy, minimum measurable accuracy. And so we certainly should expect something to be detected, right? But guess what? No matter how hard they tried, they couldn't find anything. As we rotate this device, there was no detectable fringe shift whatsoever. They didn't like that result, so they kept on refining it, kept on working hard on it, and they just got the same result, always. So, you set out to measure something and you never found it. Okay? What do? Well, they believed in their measurement. They didn't think anything was wrong with their measurement, so the measurement must be accurate. Even though they didn't like the result, they went ahead and published it. Honestly, okay, this is very important, scientific honesty, intellectual honesty. And this is the famous null result. They did not detect any movement of the Earth relative to ether as they set out to detect. So, what do you make of it? Okay, to most people, to most physicists at the time, that was a puzzling result, but to one physicist, this was exactly what he was looking for. And that physicist was none other than Albert Einstein. Okay, before we settle down to look at the details of relativity, I want to point out a couple of common myths, common misconceptions about relativity. Okay, first of all, some people thought relativity is an entirely new theory that Einstein simply dreamed of. It didn't, it was something that's totally out of nowhere. That is not true. Okay, relativity is not entirely new. It's because within classical physics itself, there were some internal conflicts, okay? Specifically between the Galileo relativity and Maxwell's equations. One of them has to be wrong because they're incompatible with each other, as we saw. Okay, some people even believed that the Maxwell's equations need to be rewritten, but Einstein chose to believe otherwise because, there's Maxwell's equations, there's really nothing wrong with it. So the Galileo relativity must be wrong. You cannot do the Galileo transformation from one reference frame to another because otherwise you're going to get different versions of Maxwell's equations in different reference frames, which violated the principle of relativity. So, relativity was a theory that was forced upon us, okay, by an internal conflict that existed within classical physics itself. For this reason, many textbooks choose to put relativity inside the E&M textbook. So in many E&M textbooks, you will have a chapter called relativity, because naturally when you study Maxwell's equations, you have to ask yourself, what happens if I use a different inertial frame to look at the same equations? Am I going to get different values or get the same physics? And Einstein said it has to be the same physics, and therefore the speed of light, which is embedded in that equation set, must not change as you go from one reference frame to another. Okay, so that's one thing. The second misconception is a lot of people thought relativity means nothing is absolute because everything is relative. Well, you know what? There was relativity before the theory of relativity. The Galileo relativity says, okay, the speed of anything, okay, is not absolute, right? Because different people would get different speeds. If you measure the speed of a car from different angles, you're going to different reference frame, you're going to different values. And the speed of light is also relative because it depends on whether the source of the light is moving or not, right? And what is absolute? Well, some things are absolute. The measurement of time, the measurement of space, which is the distance between 2 points in space, that is the same no matter who's measured it. Okay, so space and time are absolute, and speed of anything, including that of light, is relative. That is according to Galileo. But the special theory of relativity by Einstein says, no, it's the other way around. You must guarantee the absoluteness of the speed of light in vacuum. Okay? And as a result, we are forced to twist our conventional notion of space and time. It turns out that space and time are no longer absolute quantities. They must be subject to different reference frames. Different reference frames will get you different values of space, length measurement, and different measurements of time, because you have to guarantee the constancy of the speed of light in vacuum. So basically, there is relative quantities before relativity, and there is also absoluteness within the theory of relativity. Okay, it's not like we have everything was absolute, now everything becomes relative. No. There is absoluteness and relative quantities in both theories, old and new. The difference is that we have replaced the absolute space and time with absolute speed of light in vacuum. Okay? This is what we have to keep in mind. According to historical accounts, Einstein, even though the Michelson-Morley experiment was performed before Einstein published his theory of relativity, historical account had it that Einstein was not aware of the Michelson-Morley experiment, but he independently arrived at a conclusion, the same conclusion, consistent with null result. And then that has to do with the second alternative. Remember, the first choice, the first way out was to say that Galileo relativity was only confined to mechanics, and you cannot apply to E&M. If you did an E&M experiment, you're going to be revealing your true speed using the speed of light, and therefore the speed of light, just like the speed of sound, is only this value in a certain reference frame called ether, right? But that means that relativity, or the equivalence of all inertial frames, is confined only to mechanics. And Einstein did not like it. Okay? He believed that the principles, that the laws of physics, whether it's mechanical or E&M or anything else for that matter, must be valid for all inertial frames. In other words, relativity extends beyond mechanics. Okay? No matter what experiment you do, mechanical or even E&M, you are not going to be able to detect your so-called absolute speed relative to ether. You just get the same exact result. Okay. So he says the principle of relativity remains valid for all physical phenomena, including E&M. In other words, the Galileo transformation must be wrong. Because the Galileo transformation for speed will give you different value for the speed of light in different inertial frames. And yet, the speed of light must be the same for all inertial frames because it is guaranteed by a pair of fundamental constants. Okay? If you change these values of constant, you're changing the laws of physics in different reference frames. You cannot do that. Okay, and therefore, naturally, the speed of light, not other speed, but the speed of light in vacuum, must be a universal constant in all inertial frames of reference. Again, if that's not the case, then you're going to have to change these fundamental constant values, epsilon naught, mu naught, which determines the speed of light in vacuum in different reference frames. And that means in different reference frames, the laws of E and M, the Maxwell's equation, will have different results. And that violates the principle of relativity. So the speed of light in vacuum indeed is a very unique speed, unlike the speed of sound. So here is Einstein's two postulates, published in 1905. Okay, the first one is the principle of relativity. Basically, it extends the Galileo relativity beyond mechanics. Galileo relativity says that all the laws of mechanics must be the same in all inertial frames. The principle of relativity says all the laws of physics, okay, not just mechanics, must be the same in all inertial frames of reference. All right, that's postulate number one. And if you believe in this postulate, then you must also arrive at this stunning conclusion that the speed of light in vacuum must be a constant. Why? Once again, because if you say all the laws of physics must be the same in all reference frames, that must have included Maxwell's equations, right? For E and M, right? But Maxwell's equations inevitably has a speed of light buried inside, okay? It's embedded in it, the speed of light in vacuum, and there must be the same value for all reference frames because otherwise different reference frames will arrive at different laws of E and M, right? So the speed of light in vacuum must be a constant regardless of who is measuring it, okay? If you drive a very fast car at, say, half the speed of light forward towards me, and you shoot a beam of light towards me on that moving car, you might think that I would measure the speed of that beam towards me at half of c plus c, right? Which is 3/2 c. No. According to Einstein, no. The speed of light of that beam from your approaching car is still equal to no more, no less, but c. Otherwise, the laws of physics in E and M, at least, from my reference frame and from your reference frame would be different, and that would be a direct violation of the first postulate of Einstein. Okay, I already warned you, okay? We're going to have to twist our notion of space and time, not absolute quantities anymore, because we have to accommodate the new absolute quantity, which is the speed of light in vacuum. And at this point, we're going to look at three classic examples that shake up our notion, our sense of space and time. You will find for the first time that space and time are no longer absolute quantities.